Hello everyone. Today I'd like to introduce the concept of optimal power flow. You may know power flow calculation for static analysis of power system. Actually, optimal power flow, uh, the optimization concept is introduced to power flow formulation. That is optimal power flow. Optimal power flow. There are several, variants of optimal power flow in the literature uh, for its their own purposes. Here, I'd like to talk about what the optimal power flow is. Uh, to understand the optimal power flow, you need to understand the level of power system modeling. The first modeling level, it is uh, hierarchical level 1, assuming that there is only one bus, which means we neglect the network, right? So there is only one bus, several generators connected to that bus, right? And the load, the system total load, uh, is connected, right? That is hierarchical level 1 modeling. This is for adequacy analysis based on generation resources and load. The second level is hierarchical level 2. The difference between hierarchical level 1 and 2 is the considering transmission systems. So basically it considers networks, right? And so actually we need to consider the several constraints of transmission lines and other transformers and branches. Hierarchical level 3, uh, actually it considers further the distribution system, right? But the thing is, it is quite difficult to model that. Frequently, the configuration of distribution system is changed, so quite hard to model power system in this level, right? And also, we need to know the operational strategies. The first strategy is to maintain system integrity. Integrity means several components, power system components are integrated, right? So as you guys know, power system basically certain protection systems are implemented to protect the corresponding components. The environment or the conditions of the power system is changed, then the protective relay may operate to trip their own components, right? Then we can say the system integrity is broken, right? So it is really, really important, to maintain a system integrity, get them together, right? To act as like power systems or power networks. The second one, uh, minimization of load interruption, right? So it is quite important to uh, load, to supply the load, right? These two are considered as really, really important operational strategies conventionally. Uh, to operate the system properly, we need to keep a certain set of conditions. The first one is to maintain synchronism. It is related to the system frequency, right? The system frequency should be within the acceptable range. Upper and lower limit of frequency, it should be within them. The second conditions is related to voltage limits, right? Sometimes, a certain substation may experience a low voltage, sometimes high voltages condition. In the case of low voltage, motor has some trouble, right? It may stall. In the case of high voltage, there might be an insulation problem and overfluxing problem, and it results in magnetic saturation, maybe causing harmonics, right? And third one is line thermal limits. Okay, each line should have its own maximum current limit, and then we can calculate the corresponding power flow limit, active and reactive power flow limits, right? And then we need to keep the power flow within the physical limit, right? The second one and the third one, actually we can calculate, we can evaluate the conditions using the tool of PowerFlow for static analysis of power system, right? And after calculation of power flow, we need to keep the voltage level within the limits, and the line flow, whether the line flow is within the limit. We need to check them out, right? This is the basic condition. And other than that, we need to consider further other operation objectives. The first one is economic operation. We need to supply the load with economical generation dispatch. That is a really important thing. And other perspective is to minimization of power system transmission loss. And sometimes we need to keep the acceptable transfer capability, right, to maintain system security. That is also what we need to maintain. In that sense, we need to understand the security constraints. What are security constraints? In the sense of security, we can classify it into two. The first one is static security. The second one is dynamic security. So the second one can be called system stability. Just like I said, optimal power flow, the concept of the optimization is introduced to power flow formulation. The whole the formulations can be expressed in a linear programming problem consisting of objective function and constraints. Satisfying their constraints, hold the solutions, satisfying the included constraints in optimal power flow. Actually, the holder solutions satisfying the constraints. Actually, we call them feasible region, right? This is a feasible region, and the whole solution satisfying in the feasible region satisfying the constraints, and then we'd like to find the best solutions. In this case, minimizing the objective function, right? So we need to, if it is possible, to check the whole operating the operating point in the feasible region, and then what is objective function value, and then we'd like to select the best one. That is the concept of the linear programming problem, right? So basically, we can say in the feasible region, any points are PowerFlow solutions satisfying the whole operational constraints, voltage limit as I said, and also line thermal limit, right? So basically, OPF then includes the PowerFlow equations. Okay. Then we need to understand the PowerFlow equations. Basically, they are power balance equation in active power and reactive power at the corresponding node or corresponding bus I, right? PG minus PLI should be injected to the external power systems, right? If it is satisfied in active power and reactive power, that is, the PowerFlow solution. Okay, so what we need to consider, PowerFlow equations in optimal PowerFlow formulation. Okay, but the thing is, the power injection, it's a function of the voltage phasors of the neighboring buses directly connecting from bus I, right? So they are function of the voltage magnitude and angle, just like here. Okay, and then we can notice that they are including cosine and sine terms, so they are nonlinear, right? So optimal power flow includes equality constraints, right? Which are power flow equations at every bus, right? And then in power flow analysis, what are state variables? We need to calculate the voltage magnitude and angle, and what are parameters, which are control variables. They are active power generation and generator voltage setting. And sometimes we don't want to shed load, but in extreme case we need to shed some load. Of course, we need to minimizing the shed load to solve the corresponding problems. Okay, anyway, these three are considered as control variables. Okay, in the power flow calculation, after obtaining the the solution of a state variable, and we need to determine some parameters. The first one is reactive power generation and slack bus active and reactive power generation, and also we need to determine the line or branch flows. With that, we need to check whether power flows are within the corresponding thermal limit. Okay, the one of the typical point is generation bus type sometimes change it, right, from PV to PQ, sometimes PQ to PV, right, because of the resource of the reactive power support from a generator is limited. So the resource is exhausted. It is impossible to further control the voltage magnitude at the generator terminal, right? Then the bus type is changed into PQ, right? So it is quite hard to consider in OPF formulation. Okay. So in power flow, we need to assume that is a slack bus absorbing the changes of the generation, active power generation, and the generation pattern, right, might not be optimal, and also the control parameters are corrected by the operation experiences by the system operator. So the settings might not be optimal. Okay, so we need to apply OptimalPowerFlow, and here the OPF formulations is shown. This is objective function, which is to minimize fx, and then also the formulation includes constraints. The first one is inequality constraints corresponding to network equation. The second one, the inequality constraints. Usually they are operating constraints, right? So this figure shows equality constraints. Within this range, the solutions are all satisfying the network constraints, the equality constraints. This range, in this range, the points are satisfying the operating constraints, operational limits. So what is a feasible region? And satisfying all the constraints. So this is the feasible region, right? So we'd like to find the minimum objective function within this feasible region. That is what OPF does. So from this formulation, we can notice that basically they are OptimalPowerFlow formulations are nonlinear programming formulation. And then in the literature, there are several various solution techniques. And in the solution techniques, we need to deal with properly equality and inequality constraints. In this slide, I'd like to explain the objective functions. There are several OPF formulations, and hence there are several objective functions. Right? The representative OPF objective functions are the first one, generation cost minimization. Right? To keep the economical operation pattern. The second one is loss minimization. So basically, the control variables in the first one, first formulation, that is, it is PG, active power generation. By changing the active power generation of each generator, actually we'd like to find the optimal solution in the sense of generation cost minimization. Actually, for the second formulation, actually we used reactive power related control parameters, generator voltage setting, bus acceptance, and also transformer tap ratio. By changing them, we'd like to minimize the loss. Basically, the first one is called P problem. The second one is called Q problem, right? Which one is the more important? Quite hard to say, but we need to solve the P problem first about a generation pattern for economical operation, and then we need to solve the Q problem using the other control variables related to reactive power. Okay. Other than these two, there are several objective function can be used. One example of it is minimization of load shedding, or maximization of power transfer capability of the system. Right? And what are control variables in OPF? Generation voltage setting, of course, LTC transformer tap ratio, as I said here, and then switchable capacitor, not capacity, capacitor. The variable is presented with bus acceptance and fact parameters and load shedding, etc. Okay. After solving active power problem, reactive power problems are considered, as I said. And the real operation, we need to consider n-1 security, right? So then the OPF is called security constrained optimal power flow. It is one of the difficult optimal power flow formulation to solve, right? So in a real application, loss minimization problem are more applicable. Then what are constraints? As I said, the operational constraints are usually considered, and other resource constraints. So PG limits are kind of resource constraints, also QG limits, right? And operational constraints and also tap ratio limits are resource constraints of the control variable. And voltage limits And branch flow limits, they are operational constraints. And we need to consider equality constraints in the optimal power flow formulation, which are usually network equations. Right? In the concept of the OPF, usually solves one operating point, right? The solution is one operating point, right? Which means it just provides the solution for the corresponding snapshot state. Okay. When considering a -1 security, one of the system component is stripped because of the certain reason, and then that OPF is called security constrained OPF. Okay, then what are advantages of OPF? We can achieve better economy, right, using OPF. And it provides the best solution unically. And then we can find, binding constraints in the network. So in the sense of a transfer capability, which lines are transfer bottlenecks, we can identify them using OPF, right? And we can do automatic procedure when determining whether new or where new equipments are installed, right? And then several cases are investigated and then compared. And also we can do a sensitivity analysis. Certain control variables are changed or relaxed. The constraints are relaxed. Then what happened, right? How much the objective function values can be improved. We can do that, the sensitivity analysis. It is possible to formulate an LPF with redundancies for solutions to infeasible cases, right? We can deal with the infeasible cases using the slightly modified formulations, right? And we can use OPF for reference cases in a new regime and new market policy. Yeah, we can do that. These are the advantages we can obtain using OPF.